This video is a continuation of section 2.4, Simplifying Radicals. We're going to continue to simplify radicals by doing something that is called rationalizing the denominator. And then we're also going to define a conjugate binomial and use that to rationalize a denominator. So we only have two expectations left of this lesson, which is rationalizing a denominator and defining a conjugate binomial in order to rationalize a denominator. So we're going to scroll down over here and we're going to get to this right here where we actually start talking about rationalizing a denominator. All right, so here we go. A radical is considered to be in its simplest form when no radical is in the denominator. Okay. We use the term rationalizing the denominator because radicals are generally irrational numbers. So for example, if you took the square root of 2, that is an infinite non-repeating decimal, making it irrational. And generally the convention is denominators are not kept as irrational numbers. So again, if we look at this fraction right here, 1 over 3 root 2, we've got root 2 in the denominator. Root 2 is going to be an irrational number. So we don't want to have root 2 in the denominator. It's not in its simplest form. We want to get rid of this root 2 in the denominator. So how do we get rid of the root 2 in the denominator without changing the value of the fraction? So this is how we do it. So if we have 1 over 3 root 2, you will recall that we can multiply a fraction by something so long as it does not change the value of that fraction. So if I multiply this by root 2 over root 2, this is acceptable because root 2 over root 2 is just 1. So I can multiply this fraction by root 2 over root 2 because it's just 1. I'm not changing the value of the fraction. And then I'll go ahead and I'll have, okay, well, 1 times root 2 gives me root 2 in the numerator. And in the denominator, I would have 3 root 2 times root 2. Okay, well, the denominator would be 3 root 2 times root 2. That's the same thing as saying 3 root 2 times 2, which is just 3 square root of 4. Okay, well, this 3 square root of 4 is actually, we can find the square root of 4, right? 3 square root of 4 is just 3 times 2. And so I'd have 2 over root 2 over 6. And as I see right here, this is a rational number. 6 is a rational number, so no radical in denominator. All right, just to recap what I did here is I had a fraction with a radical in the denominator. This is not considered to be in its simplest form. Our convention is not to leave radicals in the denominator. So how do we rationalize the denominator? Well, I multiply this by root 2 over root 2. As you can see, I'm multiplying it by the exact same radical. And root 2 times root 2, again, that's also thinking of like root 2 squared, right? Which just produces 2. And now my denominator no longer has a radical. So how to rationalize a denominator with a monomial radical? What we're going to do is we're going to write right here, we multiply the numerator and denominator by the radical. Okay. The key thing here, though, is to see that this is what's considered to be a monomial. This is a monomial here. And it's a monomial because it's just one term. That's what we would consider a monomial. Monomial radical is just one term here. just 3 root 2. So again, how do we rationalize that? We just multiply it by the radical, numerator and denominator, and it produces a rational denominator. Now, what happens when we get to binomials? So as you can see, this is a monomial. There's no plus or minus here. There's only one term. This right here is a binomial. So we have a different situation when we have a denominator with a binomial. And that's where we have to introduce this idea of conjugate binomials. A conjugate binomial is a binomial where the second term has the opposite sign than in the original binomial. So as we can see here, this is 2 root 7 plus 3 root 5. The conjugate binomial would be 2 root 7 minus root 5. That's what a conjugate binomial is. So 2 root 7 plus 3 root 5, the conjugate binomial would be 2 root 7 minus 3 root 5. So let's see what happens when we multiply these conjugates together. Well, if we look at this right here, we've got 2 root 7 plus 3 root 5, 2 root 7 minus 3 root 5. This should start to look somewhat familiar because you should hopefully be seeing a pattern here. A plus B, A plus B, the exact same thing, A minus B. Okay, so hopefully you see this and you're like, okay, I know what this is. This is a difference of squares. Okay, so this is what we would call a difference of squares, which we've definitely seen before over the past 2 years. Okay, so if I multiply two conjugates, when we multiply them together, we get a difference of squares. So we get a difference of squares. This produces a difference of squares. So multiplying conjugates produces a difference of squares. So that means I have to now take 2 root 7, square it, minus difference of squares, 3 root 5 squared. Now remember that when you have an exponent on the outside, it applies to both. So this would be 2 squared root 7 squared minus 3 squared root 5 all squared. Okay? You don't have to have the brackets here. I can actually get rid of these. Now, the squared and the square root will cancel because they're opposite operations. Right? Squaring and square rooting is just the opposite. So then I have 4 times 7 minus 3 squared is not 3. 3 squared is 9. 9 times 5. So 4 times 7 is 28 minus 45. And the answer there is negative 17. Okay, so what is remarkable about this? Well, I had conjugate binomials. Again, conjugates because they have different signs here, plus, minus. And as you can see, there are all these radicals. Well, when we multiplied the conjugates together, that eliminated the radicals, right? It eliminated the radicals, and now we have a rational number. So why is that useful? Well, multiplying conjugate radicals, what that does, multiplying conjugate radical binomials eliminates the radicals by creating a difference of squares. So the above concept is helpful when the denominator of an expression has a binomial with radicals, making it irrational. So if we see this fraction right here, this is not an acceptable fraction because we have radicals in the denominator. We cannot apply this principle since it's not a monomial. We can't do this because the denominator is not a monomial. The denominator is a binomial. We have two terms. So what are we going to do? We are going to use the instructions above to help rationalize the denominator. Okay, we are going to multiply by the conjugate binomial here. So I'm going to take this fraction right here, 2 root 7 plus square root 5 all over 3 square root 7 minus 2 square root 5. Recall, these cannot cancel because there are basically brackets around here, so we have to do the addition in the numerator and the subtraction in the denominator before we divide. So we can't cancel these. So what I'm going to do is I'm going to multiply this by the conjugate binomial of the denominator. So 3 root 7 plus 2 root 5. 3 root 7 plus 2 root 5. Again, this is acceptable because I am basically multiplying by 1. If you have the same thing in the numerator over the denominator, that's just 1. All right? So let's multiply these out. Well, we saw already that in the denominator, we are going to have a difference of squares. We're going to have 3 root 7 squared minus 2 root 5 all squared. Again, conjugate binomials will eliminate the radicals by creating a difference of squares. However, in the numerator, we will actually have to FOIL. So we're going to multiply this right here. So multiply these two. Okay, 2 root 7 times 3 root 7 is the same thing as saying 6 root 7 times root 7. 2 times 3 is 6. Root 7 times root 7. Root 7 times root 7. Okay, that's okay. Here we go. 2 root 7 times 2 root 5 is the same thing as saying 4 and then root 7 times root 5. Let's do the next ones. Root 5 times 3 root 7 is the same thing as saying 3 root 5 root 7. Just extend this. And the final one. Root 5 times 2 root 5 is plus 2 root 5 root 5. Okay, let's keep going. Let's start by looking at the numerator here. Well, 6 root 7 times root 7, remember that's the same thing as saying like root 7 squared, root 7 times root 7, which means that this would cancel and that would cancel and we would just get 7. Alternatively, the other way of looking at that, root 7 times root 7 is the same thing as saying root 7 times 7, or alternatively, root 49, and the square root of 49 is just 7. So this just becomes 6 times 7. This here becomes 4, and remember, root 7 times root 5 is the same thing as saying root 7 times 5, again, which is the same thing as saying root 35. Okay. So this should be 4 root 35. And then plus 3 root 35. Just going to clarify, that's a 4 right here. And then this becomes plus 2, and then root 5 times root 5 is just 5. In the denominator, I would have 3 squared root 7 squared minus 2 squared root 5 squared. And we can see, as we said before, this is going to rationalize my denominator. It's going to get rid of those radical symbols. Okay, well 6 times 7, if I think about that, 6 times 7 is equal to 42, right? And then 2 times 5 is 10. So those are like terms, that should be 52. And then 4 root 35s plus 3 root 35s is equal to 7 root 35s. Okay, and then 3 squared over here, I'm just going to erase this right here. 3 squared is 9, right? And then 9 times 7, 9 times 7 is 63. Minus 2 squared is 4. 4 times 5 is 20. It's 20. So I end up with 52 plus 7 root 35 all over 43. And that's my final answer there. Okay. So just to recap here, I'm just going to zoom back in. Sorry, give me a second here. I had this fraction, which was unacceptable because I had radicals in the denominator. So I multiplied by the conjugate binomial. Conjugate binomial is the exact same binomial except with a different sign. That produced a difference of squares in the denominator. Why did it produce a difference of squares? Well, we can go back up here and we can see that if you have a binomial with different signs, that's just the formula for difference of squares. So that produces a difference of squares. And then I just FOILed the numerator. And I ended up with this final answer right here. Thanks for watching.